Let's take a look at the function f of x equals sine of x. Now we all know by now that at 0, sine of 0 is 0. Now, what happens if we change some things inside of this function, f of x equals sine of x? So the first thing I'm going to do is look at what sine of x minus 1 does. So I'm going to make my c value equal to negative 1. Notice what happens to the graph is it shifts 1 unit to the right from where it started. We're going to call that the phase shift. In other words, it starts at 0, it hops 1 to the right, even though c is at negative 1. We're going to find out later why that is. Let's look at another example. So this time, instead of making c negative 1, let's move back over and make c positive 2. In this case, again, we're starting out with sine of x for the gray graph. If we make c positive 2, then it actually shifts to the left. In this case, the phase shift would be negative 2. It would be this new x value. The graph initially started at 0, the middle of the wave, and now the middle of the wave is at negative 2. Let's look at another example. This time we're going to start at cosine of x. We know that cosine of 0 is 1. That's its initial y value. I'm going to do a couple things to this cosine function. Okay, the first thing I'm going to do is change the b value. So I'm going to make b equal to 2. Now we learned in a previous lesson that changes the period of the graph. It's kind of like a spring, and it scrunches it up as we increase b. But for now we're just going to make b equal to 2. Now notice, it does nothing to the initial value, right? But watch what happens when we change c. We're going to change c equal to minus 4. Okay, now the new top of the wave, or the new initial value, if you want to call it that, is now at 2. So if we make cosine of 2x minus 4, the new top of the wave is now at 2 instead of 0. Okay, again, we would call that the phase shift, and we're going to say that's equal to positive 2. Now, why is that? Why do these changes influence the phase shift in that way? Well, first of all, let's go ahead and define phase shift now. It's going to be the horizontal shift of a trig function from its initial point at 0. As you can see, all three of these, that purple line represents the phase shift. Now let's investigate that more closely. Let's go back to that first shift we did of sine of x minus 1. We can see that it's just the difference between these x values, which is 1. Now the algebraic way to do that is to say, okay, well, my initial x value was 0, but I've made some changes to the function. Namely, I now have x minus 1. Well, if I want to see what my new x value would be given that initial value, I would just set x minus 1 equal to 0. So if I set x minus 1 equal to 0 and add 1 to both sides, that confirms the fact that my phase shift is equal to 1 algebraically. Let's look at the next example we did. Sine of x plus 2. We noticed that it shifted 2 to the left. In other words, it's my new x value. My original x value was 0, my initial x value. My new x value is negative 2, therefore the phase shift is negative 2. Algebraically, you would do the same thing. You set what's inside the parentheses equal to 0, subtract 2 from both sides, and voila, that confirms the phase shift is negative 2. Let's look at the third example. We had cosine of 2x minus 4. We saw that the new x value, where the crest of the wave is now at 2 instead of at 0. So the phase shift is 2. Well, again, what we can do is just set the parentheses equal to 0, since we want to know what would give us that initial top of the wave. And voila, 2x minus 4 equals 0. Add 4, divide by 2. X is equal to 2. That gives us the phase shift of 2, confirms what we see visually here. In general, if we have any trig function, and this actually goes for tangent and all the other ones as well, any trig function g, so say sine, cosine, or tangent of bx plus c, all we need to do is set what's in the parentheses equal to 0, and that will help us figure out the x value, which gives us the phase shift, hence where it shifted from 0. Okay, so that will give us the x value that represents the horizontal shift of the trig function from its initial point at 0. So let's do some algebra here. If we subtract c from both sides, we get bx equals negative c. If we divide by b, we get x equals negative cb. Therefore, the phase shift is just going to be negative c over b. Simple. Now you might be thinking, well, what happens if we do if we put an a value here, which we learned before represents the amplitude, and d, which is a vertical shift? Will that at all affect the phase shift? Well, let's take a look visually at that, and then we'll make a conclusion. Okay, I'm just going to go back to the cosine of 2x minus 4. We've already confirmed that the phase shift is 2. Let's watch what happens if I change my a value. Okay, now it does stretch the graph, but still the horizontal distance between the crests of the waves is still 2. So it does not affect the phase shift. Okay, and then let's change the d value. Well, the d value just moves the graph up and down. Again, it has nothing to do with the distance between the crest of these two waves. It's still 2. So no, it doesn't. These a and d values don't affect the phase shift. The phase shift depends on the b and c values inside. And so this is just basically saying the same thing. You're still just going to set bx plus c equal to 0 because that still gives the initial value of the function. So at the end of the day, the phase shift is always going to be negative c over b. Now this makes it very easy. If you remember this formula, whatever you get is going to tell you if it moves left or right. So if after you plug in negative c over b you get a positive number, then that means the phase shift is to the right. If after you plug in negative c over b you get a negative number, the phase shift is to the left. Now that's going to be it for this introductory video for phase shift. If you have any other questions about this, let me know.